Welcome to ilectureonline. Here's an interesting problem that lends itself to using the Thevenin equivalent circuit. And by the way, that's what we're going to do and use to find the voltage between A and B. It's also known as the Thevenin voltage if we made the conversion. What's interesting about this problem is the layout of the problem. And so when we start drawing the first circuit with the source removed, in this case, since it's the voltage source, it becomes a short circuit. Now we're going to find the Thevenin impedance between A and B like this. But the way the circuit is drawn, it makes it difficult to see how to do that. And so a good idea is to redraw the circuit and make it look like this. Notice when we come from A, we get to this junction. We now have a choice to go either through the 8 ohm resistor or the capacitor. So we have to have a junction and have the 8 ohm resistor and the capacitor right here. Then they come back together. Why do they come back together? Because it appears as if this junction is not the same junction, but in actuality, it is. With the source removed, we have a short in between, so essentially this point and this point is the very same point. So that's why we come back together to this single point right here. Then from that point, we can either go through the inductor or we can go through the resistor, the 4 ohm resistor. So again, it doesn't appear that way, that from the same point we can go to these two devices. So therefore we redraw it, and here you can see that from the same point we go to the 4 ohm resistor or the inductor. Then they come back together to the same point to go to B, and that's this right here. So it's in actuality the very same circuit, and this is a lot easier to work with. So now when we try to find the Thevenin equivalent impedance, we simply have to add up the impedance of these two parallel branches. So for the first branch, we use a product over the sum. So we have 8 times a minus j6 divided by 8 minus j6. And then the second one is plus the product. We have 4 times j12 divided by 4 plus j12. So now we can write that. Now, well, we'll have to write that into the magnitude phase angle format so we can do the division. So this becomes a minus j48 or 48 with a phase angle of minus 90 degrees. And this one here, 48 again, but with a plus phase angle. So that would be 48 with a plus 90 degree phase angle. Okay, now we divide by this. That's 8, 6, well, that looks like a 3, 4, 5 triangle. So we get 10 with a phase angle of minus, so we get 6 divided by 8. Take the inverse tangent, that would be minus 36.87 degrees. Minus 36.87 degrees. Over here we get the 144 plus 16. Take the square root, 12.649. With a phase angle of, let's see here, that would be 3. Take the arctangent. We get 71.565. Okay, now we can divide them. So this becomes equal to 48 divided by 10, which is 4.8, with a phase angle of 90 minus plus 3687. Because we'll bring it to the numerator. That would be a minus 53.13 degrees. And over here we have plus 48 divided by 12.649. That gives us 3.795 with a phase angle of 90 minus 71.565. That's 18.435. Now we have to reconvert it to real and imaginary parts. So we're actually able to add these two together. So this is equal to 50, let's see here. We have a negative angle, okay? So we have 53.13, we take the cosine of that, times 4.8, that's 2.88. And then we have 53.13, take the sine of that, and multiply that times 4.8, so it would be minus 3.84. So minus j3.84. Over here, 18.435. Take the cosine of that times 3.795 equals 3.6. and 18.435, take the sine of that, times 3.795, and that's exactly 1.2. So plus J 1.2. Now when we combine the real parts, we have 2.88 plus 3.6, that's 6.48. And then if we add the imaginary parts, no, it's going to be minus. The negative part is bigger than the positive part. So we have 1.2 minus 3.84. That's a minus 2.64. And then we can convert that back to magnitude and phase angle format. 6.48 squared plus 2.64 squared equals, take the square root, I get just about 6.997. Let's try it again. 6.48 squared plus 2.64 squared equals, take the square root, I get 7 with a phase angle of 2.64 divided by 6.48. And then take the inverse tangent, 22, it's a negative angle, 22.166. All right, so that gives us the Thevenin impedance. Now let's check to see if I have that right. I never calculated that portion of it. All right, good enough. Yeah. All right, ready? Okay, so what's the next step? Next, we need to find the Thevenin voltage, which is the voltage between A and B. So now we go back to this circuit right here, and the best thing to do, well, there's different ways in which we could approach that, but one way to approach that is to say, well, we're going to have a current coming through here, which is I, and then that current will split up into I1, the left branch, and I2, the right branch, to get to A and B. So, well, you know, probably the best thing to do is to simply calculate the currents. So we have voltage, and we have the impedance of this branch. So I think that's the way I'm going to approach it. We have the voltage of the source, and then we have the impedance of the left branch, we have the impedance of the right branch. So, one way to approach it is the following. We can say that I1 can be found by taking the voltage of the source and dividing it, because the voltage of the source is the same as the voltage across either the left or the right branch, and we divide that by the impedance of the left branch. So if we do that, we get the following. We get 120 with a phase angle of 75 degrees divided by Z1, which would be 8 minus J6. This needs to be converted. So this is equal to 120 with a phase angle of 75 degrees. And then we convert that to, again, do we have that up here somewhere? Yes. That is 10 with a phase angle of minus 36.87 degrees. So that would be 12 with a phase angle of 75 plus 36.87. That's 111.87 degrees. Okay, so that's current 1. Let's do current 2. I2 is equal to voltage to the source divided by Z2. So in this case, 120 divided by 75 degrees divided by Z2 would be the impedance of this branch. And notice that would be 4 plus J12. 4 plus J12. Because that is in series, so we simply add them up, and we have that calculator right here, which is equal to this right here. So this can be written as 120, phase angle of 75 degrees, divided by 4 plus J12 can be written as this right here. That's 12.64 9.49 with a phase angle of 71.565 degrees, which is 120 divided by 12.649. That gives us 9.487. 9.487 with a phase angle of 75 minus 71.565 equals, that gives us 3.435 degrees. 3.435 degrees. Okay, so now we have the two currents, the current going to the left and the current going to the right. So what I can do now is calculate the voltage drop from here to here. And then I can calculate the voltage drop from there to there. And the difference of the voltage drops should be the voltage from A to B. So I could then say V1 is equal to, how do I calculate the voltage drop? Remember Ohm's law, I equals V over Z. So V is I times Z. So V1 is equal to I1 times Z at the top. So times Z on the left. I'll just call it Z sub L because I only want the impedance of this right here. So in this case, I1 is equal to 12 with a phase angle of 111.87 degrees multiplied times Z at the top. That would be 6 with a phase angle of minus 90 degrees. And so V1 is equal to 72 with a phase angle of, subtract 90 from that, that would be 21.87 degrees. So that's the voltage at this point right here. So let's call it V1, which is V at A. So this is also V at A. Well, no, we need to be careful here, because V at A depends, of course, on what the source voltage is. So VA would literally be the voltage at this point, which is 120 with a 75 degree phase angle, and now subtract the difference between there and there, which is V1. So V1 is actually the delta voltage. So maybe I'll call it the change voltage from here to here to be technically correct. I think I'd rather write it like that. So it's the change in the voltage from there to there. Here the voltages are the same. Here they will be different from one another. Okay, because the delta V will be different. So delta V2, I like that. Delta V2 is equal to I2 times Z on the right. So again, I2, well, it's a different current. It's 9.487 with a phase angle of 3.435. And we multiply it times Z on the right, which is 4, with a phase angle of 0 degrees. So this is equal to 9.487 times 4. That gives me 37.948. 37.948 with a phase angle of 3.435 degrees. So that's the change in the voltage going down the right side. So now I can say is that volt AB, so let's see which one is bigger. This one is bigger than that. So maybe I'll do it like this. So the voltage from A to B then simply is equal to the change in the voltage 1 minus the change in the voltage 2. I simply subtract the two from one another. Okay, so there appears to be, well, let's see here. There appears to be a bigger drop on the left side and a smaller drop on the right side. Well, we'll just leave it like this. Okay, so the difference in the voltage is equal to, that would be 72 with a phase angle of 21.87 degrees. And from that we subtract 37.948 with a phase angle of 3.435 degrees. Okay, again I have to convert to real and imaginary parts. So this is equal to 21.87, take the cosine of that and multiply it times 72. That gives me 66.82 plus J, 21.87, take the sine of that, times 72, that gives me 26.82. 26.82. All right, that's the change in voltage on the left side. Then we subtract from that 37.948. Oh, let me reverse that. Let's go to 3.435. Take the cosine of that. It's always a good idea to do the same thing each time on your calculator so you're less likely to make mistakes. So times 37.948 equals, that would be 37.88. Okay, 37.88, and that's plus J. 3.435, take the sine of that and multiply times 37.948 equals, and that's 2.27. 2.27, like this. But remember, we're subtracting both of these terms from these two right here. So this is equal to 66.82 minus 37.88, and that would be 28.94, and that would be plus J, because this is smaller than that. 26.82 minus 2.27, that gives us 24.55. And now again, converting to magnitude phase angle format, 28.94 square plus 24.55 square equals, take the square root, that gives me 37.95, 37.95, not 59. 95 with a phase angle of 24.55 divided by 28.94, and take the inverse, let's see, inverse tangent, 40.31 degrees. And that's the voltage, V, voltage from A to B. So again, there's different ways in which we can approach this particular problem. But again, the general approach is you first remove the source. In this case, since it's a voltage source, we make it a short circuit. We calculate the impedance, the Thevenin impedance. Then we go back and we restore the source. Now we need to find out the voltage between A and B, which essentially is going to be the Thevenin voltage. So this is equal to V Thevenin. And we did it, not done it, but did it by calculating the current through here and the current through there by taking the total voltage divided by the impedance on the left side, the total voltage divided by the impedance on the right side. Once we have the two currents, we can find the voltage drop here and the voltage drop there, and the difference in the voltage drop is going to be the voltage between A and B, which is therefore the Thevenin voltage from A to B. And that is how it's done. Let's hope it's correct. Let's see here, 37.95 and the angle of 40 degrees. Hey, there we go. Oh, did I mess up? Oh, yes, okay. Okay.
Am I quitting?
No, you don't need to quit, but I need to make one caveat, one change. They started at the same point, same voltage point. The voltage drop here, the delta V1 was bigger than delta V2. So since the voltage drop was bigger here than it was there, then this will be at a lower voltage and this will be at a higher voltage. So when we go VAB, that's lower voltage, that's higher voltage, I really need to take the negative of that. So that would be, if you want to be technically correct, the negative of that. And so we should really put brackets around it and say the negative of that. And so here again, we take the negative of that, and again, we take the negative of that, and the negative of that, which means that we should add 180 degrees. So if we take 40, well, we can just add it in. So this is equal to 37.95 with a phase angle of, at 180, that would be 220.31 degree voltage. And that would be technically the correct voltage. So yeah, I was thinking about that initially, and I did get myself into trouble realizing now that we have a bigger voltage drop here. This is at a lower voltage than this. So essentially that's the negative of the result that we got when we took the difference. So technically I was off by 180 degrees, but now it's correct.